Hi students, in this video let us discuss reactivity of some alkyl halides in SN1 reactions. So SN1 reaction is a unimolecular nucleophile substitution reaction. It involves two steps. The first step is the formation of the alkyl halide. It is a rate determining step. It is a very slow step. And second step is a very fast step. Okay, because it is the interaction between the two ions. Now here, the dissociation of alkyl halide is a slow step and the overall rate of SN1 reaction depends on this step only. Okay, so the alkyl halide which can produce a stable carbocation are readily involved in a SN1 reactions. Okay, I am repeating again. The alkyl halides which can produce a stable cation are readily involved in a unimolecular nucleophilic substitution reaction. Okay, because intermediate is a carbocation. If higher the stability of the carbocation, higher the rate of this slow step, so then overall rate of reaction increases. So finally, simply, the rate of SN1 reaction depends on the stability of the carbocation. The alkyl halides which can produce a more stable carbocation are more reactive in SN1 reactions. Here in this case, so generally, that tertiary alkyl halides readily form a carbocation. That means here those are readily involved in a nucleophilic substitution reactions because tertiary carbocation is more stable. So that's why generally tertiary alkyl halides are more reactive in SN1 reactions than the secondary alkyl halides, and primary alkyl halides are least reactive. Now let us discuss the reactivity of these alkyl halides in SN1 reaction. So here in this case, this alkyl halide on dissociation, the producer allyl and secondary carbocation. Okay, and this alkyl halide on dissociation first produce a secondary carbocation. Now here also the secondary carbocation. Now here in this case, this one produces a primary carbocation. The primary carbocation is very unstable, so this alkyl halide, this primary alkyl halide less reactive in unimolecular nucleophile substitution reaction. This is the least reactive. Okay. Now here among these, it is a secondary, it is also secondary. Now here in this case, it is a secondary ally. It is stabilized by the conjugation with pi bond. Okay, and here in this case also it is stabilized by the conjugation with the pi bond, but here there is additionally plus some effect from this methoxy group. So here the plus some effect of the methoxy group stabilize the carbocation more. That's why here the compound 3 more reactive, and next first one more reactive, and then here second one, and least fourth one. Okay, that is the reactivity order, because this carbocation is more stabilized by the plus some effect of the methoxy group. Here in this case, just of course here only methyl groups, so methyl groups exhibit the hyperconjugation effect, but here in this case there is a resonance effect from the methoxy group. That's why this is a more stable carbocation, so it is readily involved in a nucleophilic substitution reactions. That's it. And next, yeah, in this case, produce a tertiary carbocation. Of course, it is stabilized by the resonance with the benzene. Here also tertiary carbocation after dissociation. Here also produce a tertiary carbocation. But here in this case, this carbocation is destabilized by this NO2 group, because this NO2 group is a minus M group. So here in this case, this minus M group, let's see the resonance in this carbocation. Yeah, here in this case, it is a tertiary carbocation, but it is destabilized by this NO2 group, because this NO2 group is electron withdrawing group. The pi electrons are transferred towards a NO2 group. So as a result, at this para position, positive charge is rising. So here already positive charge is there, so positive more repulsion. That's why it is destabilized by the minus M effect of the NO2. Okay, but here in this case, in a second case, that carbocation is more stabilized by the plus M effect of this one. Okay, so here in this case plus charge, here pi bond, here pi bond, this one pi bond. So here see this one OCH3. This OCH3 is a plus M group that donate the electron density. So as a result, here negative charge is rising. So here the positive negative adjacent each other, so it is more stabilized. Okay, but of course here this carbocation is not stabilized, not destabilized by any other group. So that's why here the second compound is more reactive, next first compound, and least third compound. Okay, that's it. Now here I want to add some more information here. First, suppose I am taking like this. This is the benzyl bromide. Okay, here this one is the CH3 group, and next this one also benzyl bromide. Here I am taking OCH3 actually. OCH3. Now this OCH3 at the meta position. Okay. Now this CH3 at the para position. Okay. And next here I am taking another one structure. So this is a very interesting in this case. So CH2Br and this is the OCH3. Okay. So here in this case, let's see here I'm adding one more structure. This is a benzyl bromide. This one is a CH3. So actually here in this case CH3 plus psi effect at the para position, the plus psi effect and plus H effect, and here in this case OCH3 at the meta position only minus psi effect. Here in this case minus psi effect as well as plus some effect. Okay, of course here also the plus some effect is working with benzene ring. Okay, plus some effect is working with the benzene ring, but here that is not working with this positively charged carbon. That means here, for suppose in a dissociation, this one, your CH2 plus, okay, and here OCH3. This OCH3 donating electrons. So as a result, at ortho position, electron density increases, and next year at this para position, electron density increases, and next year at this ortho position, electron density increases. But here the positively charged carbon, attached carbon, is not gaining any charge. That means here that plus some effect of the OCH3 is not working with this positively charged carbon. But in this case we can see the plus some effect of the OCH3 working with the positively charged carbon. Okay, that means its donating nature is that means this donating nature working with this positively charged carbon. But here in this case here, its donating nature is not useful for this stability of this carbocation. Okay, that's why here in this case only minus effect is considered. Of course in this case also minus effect is working, but here this plus some effect is dominating at the para position, and at the ortho position minus effect is dominating. At the meta position minus effect is dominating. That's why in this case this carbocation is the least stable. Okay, now than this one, this carbocation is more stable because of the hyperconjugation. This CH electrons, the CH sigma bonding electrons are delocalized. As a result, at ortho position negative charge is rising, at the para position negative charge is rising, more stable. And here at the CH also same, hyperconjugation effect is not working with the positively charged carbon. That's why only plus I effect is considered. When compared with this carbocation, here this carbocation least stable. So here for these four compounds here, fourth one is a more reactive because your plus some effect is dominating, and next year second compound is more reactive, and first compound, and then least third compound because OCH3 at meta position minus effect is working, minus I effect destabilize the carbocation. That's why it is a less reactive compound. Okay, that's it. So next you see this is a very interesting one. This one, here in this case, actually you can see that reactivity of these compounds. So here in this case, by leaving out this bromine, okay, here we can get the aromatic cation. Okay. See this one here, plus charge here, aromatic cation is a highly stable carbocation. That's why this alkyl halide is more reactive. The first alkyl halide is more reactive. Next here, the leaving of this Br. This is the anti-aromatic carbocation, very least stable anti-aromatic. Now here in this case, this cation is stabilized by the resonance with two pi bonds. Of course, here also this cation is involved in a resonance with two pi bonds, but here due to cyclic cation, this one has a anti-aromatic nature. 4 pi electrons are there, least stable cation. It is not involved in a substitution reaction. Okay. Now here in this case, this cation is stabilized by the two pi bonds. It's not an anti-aromatic. It's not a cyclic compound. Now here we are leaving this is the carbocation. Okay. Next here the Br leaving this is the carbocation, but this carbocation is destabilized by the CF3 minus I effect. Okay. So finally the 2 is more reactive and third one more reactive, and next fourth one more reactive, and fifth one and least anti-aromatic species least reactive. Okay. So finally aromatic cations more stable. So those are alkyl halides which can produce the aromatic cation on dissociation, that is a more reactive in SN1 reactions. And next here this is a one more question based on the plus M effect of the methoxy group. Here Br minus leaving this cation stabilized by the plus M effect. And next in this case, just we'll get the tertiary carbocation. Next in this case, we'll get the secondary carbocation. In this case, tertiary as well as it is stabilized by the plus M effect of the oxygen. So D is more reactive, next A more reactive, and B and least is a C. Okay, that's it. And next in this case, yeah, here tertiary benzyl more reactive, this carbocation more stable. It's not a benzyl, but it is a secondary cation after dissociation. Now it produces a tertiary cation after dissociation. Now here in this case, this halide is not involved in a substitution reaction. Aryl halides are not involved in substitution reaction because these are stabilized by the resonance. As a result of this resonance, this single bond becomes a double bond. That's why it's not readily dissociated. So it is stabilized by the resonance. Okay, D is the least reactive among all, and here finally C more reactive, and tertiary A, and then B and D least reactive. Now here just here already we discussed this type. Here this is the aromatic cation, this is the anti-aromatic cation. Anti-aromatic cation least stable. That's why this halide is a very least reactive. This aromatic cation more. Oh shit, here in this case you can see here just you are missing this one. Yeah. Aromatic cation, this is more stable. Okay, aromatic cation more stable, so it is readily involved in a substitution reaction. Here this aromatic cation is more stable than the benzyl carbocation. Okay, so here the reactivity order is 2 more reactive, and then 3 and then 1. Okay, that's it. Yeah, see this one is a very different question. So this is a tertiary alkyl halide carbocation, tertiary carbocation. Here we can get the tertiary carbocation. Here also we can get the tertiary carbocation. But in this case, actually the carbocation is not exist at the bridgehead carbon from the Brett's-rule. Okay, we can see the Brett's-rule. The Brett's-rule saying that bridgehead carbocation is not exist. That means at the bridgehead atom planarity not exist. Carbocations are planar in shape, so here planarity not exist at this one because it is a closed ring. Okay, but here with increasing the bridge length we can see the positive charge at the bridgehead position. So here in this case bridgehead length just only one carbon, so it is a very least stable cation than this one. So here we can say reactivity order this one. Okay, So here the similar question, this tertiary alkyl halide is a more reactive, and here in this case bridge length or increases. So with increasing bridge length, planarity may exist. Okay, here in this case just two carbons, here only one carbon. So it is a reactive order. We can see this is a experimental order given. Just I have collected from the Google. So it's a reactivity order. So this is one of the interesting point. With increasing bridge length, the carbocation at bridge head carbon we can see. And next here, this one very interestingly, here Br minus leaving, this is the cation. Okay, here Br minus leaving, this is the cation, and this one also same. Here very interestingly, it is alkyl bromide and alkyl iodide. Between alkyl bromide and alkyl iodide, here alkyl iodides are more reactive. Okay, now here very interestingly, these two cations are stabilized by the plus sum effect of the NME2. That means here nitrogen has a non-bonding electron, so plus sum effect is working. Here also plus sum effect is working. But very interestingly, due to steric hindrance between the NME2 and this is the methyl. Okay, this is the methyl. Here plus sum effect is not working with the benzene ring. Nothing but Sur effect. Okay, so because of the repulsions between methyl and NME2, that NME2 go out of the flame from the benzene ring. That's why the resonance is not happening. So the main condition for the resonance, the groups must be in the same plane. So here plus sum effect of the NME2 is not working. So it is not, this carbocation is not stabilized by the plus sum effect of the NME2. But in this case, first and third cases, that carbocation stabilized by the plus sum effect of the nitrogen. And here alkyl bromide iodides. Iodides are more reactive. So that is a reactivity. Okay, it's nothing but Sur effect, steric inhibition of resonance. In a second case, we can see. Yeah, this one just you can give the answer in a comment box. Yeah. So again, just going to the one previous question. Okay, last year 2020 JEE-MAIN question. So which of the following compounds will form the precipitate with aqueous AgNO3? Okay, so generally with aqueous AgNO3, with silver salts, SN1 reaction is promoted because here the dissociation is promoted by the silver salt. Halogens, that silver has a strong affinity towards the halogen. So here that Br minus readily going with the Ag plus. So as a result, we'll get the carbocation. Now here this carbocation stabilized by the plus sum effect of the oxygen. Now in this case also Br minus leaving, this is the carbocation. Okay, of course it is stabilized by the plus sum effect of the nitrogen. Okay, next in this case Br minus leaving, it is stabilized by the plus sum effect of the nitrogen. Yeah, here no plus sum effect from the nitrogen. It is not in a proper conjugation, so least stable, it is a least reactive. Now here if coming to the plus sum effect of the nitrogen and oxygen, the plus sum effect of the oxygen very less when compared with the nitrogen. So here 2 and 3, between these two, one is a more reactive. But here this is a very weak plus sum effect because this lone pair of electrons also involved in a conjugation with the benzene ring. That means here nothing but cross conjugation because this lone pair of electrons are involved in a conjugation with this carbocation and with these pi bonds. So here the effect from the nitrogen plus sum effect is very less on this positively charged carbon. Okay, but in this case here the nitrogen only involved in conjugation with this positive charge. Okay, it's nothing but cross conjugation, we can say. It is just a conjugation with the positive charge. That's why here this is a highly stable carbocation. So 2 is a more reactive, that readily form a precipitate. And next here one more question, similar question, AgNO3. Here also based on the carbocation stability, by leaving out the Cl minus, we can get the aromatic cation. 2 pi electrons, aromatic. Here also aromatic 2 pi electrons, but here this cation additionally stabilized by the plus sum effect of the methoxy group. Okay, that's it. Now next this isopropyl chloride and this NO2 group minus A effect is working, so destabilize the carbocation stability. Okay, here in this case a secondary carbocation when compared with the fourth one, the C carbocation more stable because of the minus effect. So ultimately here A is more reactive. Sorry, B is more reactive. Here printing mistake. B is more reactive. So option 4. Okay, you can easily answer this one because here B only one option given, B, A, C, D. That's it. Yeah, this one also one of the previous question, 2019 April online question. Okay, so in this case, I minus leaving will get the benzyl carbocation, and here I minus leaving benzyl carbocation. But here methoxy group at the meta position. Okay, as you said at initially, here minus effect is working at the meta position. Now here I minus leaving this methyl at the para position. So here the plus H hyperconjugation as well as plus I effect is working, and here methoxy group. Okay, so methoxy group working plus some effect and minus I effect, but here plus some effect is dominating because it is at the this one para position. So here this one is a highly stable, D more stable carbocation, and next C, and then A and B is least reactive. So here D, C, A, B. Yes, answer B. Just based on the conjugation. Yeah, this one also one of the previous question we can see. Yeah, in this case, Cl minus leaving primary carbocation. Here Cl minus leaving primary carbocation, and of course this cation is stabilized by the plus M effect of the methoxy group, and this carbocation more stable benzyl carbocation, and finally here the alkyl had C more reactive. Okay, and then D is more reactive. Between A and B, actually here two options are given. So first C and D here. First C and D. Between C and D, one option is correct. But in this case, A and B, which is more reactive. Here we just we get confused. Here in this case, primary halide, it is a primary halide. But here this primary halide immediately rearranges to tertiary. This primary carbocation immediately rearranges to the tertiary carbocation. That's why here little bit this alkyl halide is more reactive than this ethyl chloride. So here finally answer is C. Okay, that's it. So here in this case we can just I want to give one more more information. So just here based on the conjugation, you can see this one. So first suppose yeah, this is the alkyl halide. This one is the double bond. Here OMe group. Okay, and for suppose this is the alkyl halide, and this is the MEO group. Okay, now here between these two, which is more reactive in SN1 reaction? Now here just check the stability of the carbocation. Yeah, this is the carbocation after dissociation. Now it is stabilized by the only pi bond, but no conjugation with the plus M, that plus M group OCS3. But here in this case, here plus charge is a positive charged carbon stabilized by the pi bond, as well as it is also in conjugation with the plus M group, that is a methoxy group. Okay, so it is nothing but linear conjugation, more stable. That's why this alkyl halide is a more reactive. Okay, that means here this methoxy group is not in conjugation with this positively charged carbon. Okay, that's it. And here finally just I want to give some information about the reactivity order of the different alkyl halides in SN1 reaction. Okay, you can see this one. Tertiary alkyl halides are more reactive in SN1 reaction than the allyl halides. Okay, then the allyl halides. Tertiary alkyl halides are more reactive. That's it. Thank you. Thank you for watching. Please subscribe my channel and share to your friends, those who are preparing for JEE mains and the JEE advanced exam. Thank you.